Okay, normally we be about 50 people, but I suspect that we may not get there. This is a slightly technical subject. The lecture that I will be discussing. This is slightly technical subject. The lecture that I will be discussing. I can hear an echo. I don't think it's my microphone. Does somebody from NPTEL know? I can hear an echo. I think it's my microphone. Somebody needs to be muted. Yes, Mohan K. Yes, please could you? Or hold on, I can switch off. Somebody needs to be muted. Yes, Mohan K. Yes. Please. I'm going to, yes. All right. I have muted everybody and disallowed you to unmute. Hope that's okay. All right. I think that this is better now. Yes. So data visualization and analysis, a bit of a technical subject. Maybe that's why I think not as many people have viewed the lecture, and I don't expect as many people as normal to be here today. But certainly, if you're in the research stream, you're interested in research, interested in analyzing data to extract some kind of meaning, some kind of knowledge about the world, then you do need to get into the details of analysis and visualization. And so the lecture this week was in that spirit. And of course, it's just an introductory lecture. There's a lot more detail to go into. So if you found some of the parts hard, the maths and so on, or how we got from one place to another, I think it's necessary to sort of struggle through it and make sure you understand the steps and you understand the logic and the flow, and also some of the, if not the derivation of the formulas, at least the spirit in which they are meant. Why, for example, precision is directly related to variation. Sorry, I should say uncertainty is directly related to variation in the population, but inversely related to sample size. So you need to understand why exactly that formula takes the shape it does, but you should understand that why it makes sense for one to be in the numerator and the other in the denominator. So let's see how things go. We may have a shorter session today. I will firstly, I have to apologize that if you have filled out the Google form, which was sent out in advance, a couple of days in advance to ask questions, it looks like we don't have that results. I mean, the responses in that form. Oh, maybe we just did. Okay, there we go. Let me just see if I can find it. Okay. Let's see. We'll keep those for the end. We'll start with a couple of questions that came into the discussion forum, one of which I've answered. There are a couple of others. So one is about the bootstrap. And I can't read it. The question is long. I can't read it out exactly, but it's basically asking how does using the bootstrap how does it figure out, how does it serve the purpose of finding out what's happening, multiple sampling in an actual population. And let me just start by saying that our purpose is to understand how understand the precision of our estimate, right? So we sample one set of entities, and we have, let's say, p-fowl with their train lengths, and we find that our average train length in our set that we sampled is whatever, 110 centimeters. But as explained in the lecture, we don't know whether that 110 centimeters is far or near the actual population mean. And one way to try and estimate that, whether it's far or near, is to imagine what would it look like if we had multiple samples from the same population. How would the means of those samples differ? Are all of those means going to be clustered around 110? Or is the variation so much that we could get very different means? And so, but we have only one sample, right? We don't have multiple samples. And so we have to do some kind of, we have to make do with what we have. And bootstrap literally means pulling yourself up by your bootstraps. That's making do with what you have, essentially, is what the word bootstrap means in this context. And whether or not you do the bootstrap, you can also calculate it. The way I said, if you assume that the possible means that you could have got if you had sampled multiple times, if the distribution of those possible means you could assume to be normally distributed, then we can try and directly calculate how different those means could be based on the variation we see in the population, based on the standard deviation that we have. And so the bootstrap is just another way of doing it. We know we have only this sample of, let's say, 30 peacocks. And the basic procedure in the bootstrap, as you know, is we just take those 30 and we sample with replacement. It's like writing the tail lengths down on 30 chits of paper, putting them in a basket, and then taking them out one by one, writing them down, replacing it, taking another one, writing down, replacing it, and so on. Because those 30 individuals are our best guess for what the population itself looks like. And if the population is very variable, then every time we take a sample of 30 with replacement and calculate the mean, and we do that again and again and again, those means are going to be quite different from one another. But if all the train lengths are between, let's say, 105 and 115 centimeters, then pretty much every mean that we calculate will be very, very close to the one that we originally got, which is 110. And so looking at the distribution of those bootstrap means, we get an idea about how different the sample mean would have been if we had sampled from the population repeatedly. But do remember, we are pulling ourselves up by our bootstraps. We're making do with what we have, and all that we have is those 30 individuals. We don't have any other information. If we had other information, then we would add those in. If we had sampled 150 PFOG, then we would have put them all into that basket. There's lots more that you can read about the theory of the bootstrap, which of course it's a bit much for us over here. But remember that the overall purpose, and that's really the primary thing, the overall purpose is to understand that when we calculate the mean from a sample, we don't know that whether that mean is close or far from the true underlying population mean. And therefore, we need to calculate this precision, the standard error or the confidence interval, which tells us what confidence we have that this sample mean that we've calculated is close or not to the population mean. Some people make the mistake that they say, well, I've sampled PFOL, so there are 30 that I sampled, and I got a mean of 110, so that must be the mean. That's the actual mean of the population. But we sometimes forget that. We forget that we're only sampling a small fraction of the population. And so the actual population could very well be very different from the sample mean, depending on the things that we talked about, depending on the variation in the population and depending on our sample size. We have to approach this with some humility. The statistic that we calculate, the sample mean, we have to be rather humble about it and not claim too much about it. So that was in response to the question about the bootstrap. And let me just find the discussion forum. Yeah. And there was a question about degrees of freedom. Why is degree of freedom preferred over sample size? And what are the advantages and disadvantages? And are there specific conditions where one is preferred over the other? So again, there's sort of statistical theory that goes into this. I think that rather than explore that in detail, the thing to say is that if we were to use, for example, while calculating the standard deviation, if we were to use n, that is the total sample size, rather than n minus 1, which is the standard, which is the degrees of freedom, the degrees of freedom, to remind you, takes into account the previous parameters that we've estimated upstream before we come to this calculation. So because we first have to estimate the mean, and in doing so, we remove 1 degree of freedom, use up 1 degree of freedom, as was discussed explained in the lecture. Therefore, in the standard deviation, we use the n minus 1 because we have lost 1 degree of freedom. And if you do not do that, then basically you come up with a biased estimate of the thing that you're trying to estimate, which is, in this case, the standard deviation. So the overall, what statisticians have found is that if we make these calculations, taking into account the degrees of freedom that have been used up, and therefore using only the remaining degrees of freedom in the calculations, then we come up with an unbiased estimate of the thing we're trying to estimate, in this case, standard deviation. If we were to use n, then our measure of standard deviation would be too small, and therefore we must use the degrees of freedom. If we use n minus 1, then our estimate of the standard deviation is not inherently biased to be too small. And I think I'll just leave it at that. I think, Devika, you've sent... okay, great. Okay, there is a question which is actually, it's asking for the answer of one of the assignment questions, which of course I can't give you. Sorry, we can discuss this later. We posted in the discussion forum, then I'll answer it after the due date for the assignment. And the second question that I have here on the spreadsheet is how to select the best statistical test on the basis of sample size to compare the different types of habitats. So if you've noticed in my lecture, I've not used the word test or statistical test, and that's because to my mind, that's an advanced topic, even though it is taught at the very start. I can't say much more about it without going into an entire lecture about what is a statistical test, why do people use them, in what circumstances, and why you should actually not use them, which is my philosophy on this. But just leave it at we have not covered statistical tests, so this is out of syllabus, as they say. All right. Okay, so what's remaining is the questions in the chat box. So I'll get to them now. How can we overcome small sample size for data acquired from secondary sources like eBird? I don't know what you mean by overcome small sample size. If there is a small sample available, then there's nothing you can do. You have to just deal with it. And dealing with it usually means you have to be comfortable, therefore, with a low degree of precision. That is, your confidence intervals will be wide, and you will not be able to make confident statements. You'll not be able to make very sort of, without repeating the word confident, I don't know how to say it. You can't make strong statements about the phenomenon that you're interested in. So if you say, I've sampled peafowl and my best guess for the average tail length is 110 centimeters, but the confidence interval is 50 to whatever, 160, then you just have to be comfortable with that. You basically don't know what the tail length is. You have such a broad confidence interval but if you have confidence interval between 105 and 115, then you can make very strong statement. Yes, I know that the tail length is really in this very narrow distribution. That is the true population tail length. And just remember all the time that we're trying to infer something about the actual population value, even though we're sampling only a small fraction of the population. And you can do that. That's the magic of study design in statistics. You can make generalizations about the overall population with a sample, but it has to be done carefully, obviously. So data acquired from secondary sources like eBird. So usually we think of large data sets like eBird as actually not suffering from small sample sizes. When you go out and collect data in the field, you are going to have small sample sizes. You're going to be able to run 30 transects, or you're going to do a week of sampling or a month of sampling. But in some of these large data sets, you have millions and millions of checklists. And so for many things, you wouldn't have small sample size. But of course, if you break this down by species and by geography and by year and by season or by month or by week, then gradually, quite quickly, something that has a sample size of 1 million can very quickly get cut down into sample sizes of less than 1,000 or 100 fairly quickly, depending on how you slice the data or what kind of subset of the data you need to look at. But there's no way to overcome it. The only way to overcome it is to have more data. Either you collect more data or you wait for there to be more data in the secondary source. To keep it simple, can we remember percentiles as numbers between 1 and 100 and quantiles as numbers between 1 and 10? Yes, I think I didn't say that explicitly, or maybe I did. Percentiles are indeed out of 100. That's what they call percentiles. Quantiles are probabilities. They're, so what's the probability of a data point being less than some number? And if you're at the 9.9 quantile, then the probability of any number being less than zero point 0.9 is 0.9. Sorry, less than that number is 0.9. So think of quantiles as probabilities and percentiles as percentages. That's fair enough. Could you re-explain under what circumstances we use a z-scores and when to use a t-distribution? So really, because I don't have any visuals in front of me, I would really suggest you go back and re-look at that, the few minutes of lecture where I talk about that. The quick and broad answer again is that any set of data can be grouped into a frequency distribution. Like we discussed in the lecture. And any frequency distribution can be expressed in like a smooth line, roughly, which we call a probability distribution. And so those probability distributions, of course, can have any shape, but there are a few well-known probability distributions that are similar to many of the actual empirical distributions. So these are theoretical distributions. This is the normal distribution is a theoretical distribution, but it turns out that a lot of real-world data looks very similar to a normal distribution. And if that is true, then we can use some of the known properties of this theoretical distribution to infer something about the distribution of real-world data. So the normal distribution has a particular shape, and if we know which is defined by the mean and the standard deviation. And if you know the mean and standard deviation, you can just plug it into the formula and you can get a nice curve that shows the normal distribution. The t-distribution looks very similar to a normal distribution, except that it has more probability on the tails away from the mean. So it's a broader distribution than the normal distribution. So even if you increase the standard deviation, you know that if you increase the standard deviation of normal distribution, it gets flatter and flatter and there's more weight at the tails. But the t-distribution has even more probability or weight at the tails. And what is known is that if we, so remember we're using the properties of normal distribution when we are trying to infer something about the distribution of different possible means that we get. If we have a sample from a population of 50, and we can do this, you can do this on a computer if you're familiar with programming and know a suitable software. You can take 50 numbers at random, calculate the mean, 50 numbers at random again, calculate the mean, 50 numbers at random again, calculate the mean, store all those means, and then plot the distribution of those means. And those means, the distribution of those means will follow a normal distribution, typically, given that the assumptions of or the conditions of the central limit theorem are met. That the distribution of means will follow a normal distribution with the particular mean. That's an overall mean, a mean of means, and a particular standard deviation. And that distribution will look almost exactly like a normal distribution. But if you have a small sample size, and on your computer, if you instead draw a sample of 10 or 15 only, rather than 50, and calculate the mean and do so again and again, then the distribution of those numbers will not quite follow a normal distribution. There will be more extreme values, and those more extreme values are captured using the t-distribution, which becomes fatter and fatter at the sides, at the extremes, the smaller your sample sizes. And that's why the t-distribution its shape depends on sample size or degrees of freedom. The normal distribution does not. Normal distribution is the same regardless of sample size. So just even if that doesn't interest you and it goes over your head and you don't care to learn more about it, the lesson from all this is that when you're calculating your confidence interval and you need to multiply to get the 95% confidence interval, you need to multiply some multiplicator with the standard error. If it's a normal distribution, it will be 1.96. But if your sample size is less than 30, you have to use a different number than 1.96, a larger number than 1.96. That number is something you get from the t-distribution, because that number gets larger and larger the smaller your sample sizes. Therefore, your confidence interval also becomes larger and larger the smaller the sample sizes. So your confidence interval becomes larger for two reasons. with small sample size. One is that the standard error increases, because remember in the formula for standard error we have root of n in the denominator, and it increases for another reason, which is that your a distribution of means follows a t distribution, not a z distribution, and so both those compound together when you have a small sample size to increase the confidence interval, which is the same thing as decreasing the precision. The first question, to add to the previous question, let's say eBird data does not have species for multiple species studies during a particular time period. I don't particularly understand exactly what you mean, multiple species studies. But the bootstrap is not a trick to overcome small sample size. There is no trick to overcome small sample size. Small sample size is small sample size. And if you have a small samples, perhaps you shouldn't be doing the study or shouldn't be doing the calculations, because you can't learn very much from small samples. As we've discussed in the study design, small samples can also be biased. That means they can be highly misleading. They can be very far from the actual mean. Not just because we have a small number of numbers, but because we are very unlikely to get a representative sample of the population as a whole. So I'm afraid there's you just have to live with a small sample size, and there's nothing you can do to correct it, as I say, apart from trying to get a larger sample size. Follow-up question on degrees of freedom in the discussion forum. Fine. What are the right questions to ask? Trying to study the number of bird species during lockdown was higher compared to post-pandemic. Let's say we decide to conduct the study based on eBird data collected daily during this period on a single location. Okay, so since we don't have a flood of questions, we can go into this question here from Deepak. Is it's not only about this week's lecture, but also about my previous lecture on study design. And this is a nice example to choose. We want to know if a bird species observed during lockdown was higher than in normal periods of time. So the first thing to understand is that we have to make a fair comparison. So, example of our first lockdown was in April, May of 2020. Now, and we have eBird data, like he says, and we have eBird data up till March, right, or the previous year. We also have eBird data in April, May, and beyond that, and so on. Now, what we should not do, because it's not a fair comparison, we should not compare, let's say okay, so let's look at the analysis. In eBird, people make bird lists and they upload. And one thing that we can ask is for a particular place, let's say I'm in Delhi, in a particular part of Delhi, and I want to ask, what is the average number of species that people cite in a typical eBird list? How many species are reported in a list? And I can calculate that for February, March of 2020, before lockdown, and I can calculate for April, May of 2020, which is during lockdown. And I can look at there's a difference in the average number of bird species reported in eBird lists during that time. Now, that's not fair, or that's not a useful comparison, because the seasons have changed, right? And in February, March, we still have some migrants left, and it's possible that not only are there more bird species in that season, or fewer bird species, doesn't matter which way, but also the behavior of those birds might change. That is, if let's say February, March is the breeding season or beginning of the breeding season, there's lots of singing and activity. And then April, May is during the breeding season, like when the birds are actually nesting, and maybe there's depressed activity. So for both reasons, we could get lower number of birds sighted in the lockdown period than before, but not because lockdown had any effect, but just because the seasons have changed. And therefore the bird numbers and behavior has changed. So we have to make sure that we have an honest comparison. And so one honest comparison, you could imagine, if this was a classroom in front of you, I would have asked you, what do you think is a good comparison, given what I just said? But we can't do that, unfortunately. But I just say that, one possible comparison would be April, May of 2020 compared with April, May of the previous year, 2019. Correct? So the season, we're keeping the season the same. Of course, the year has changed. And we just have to hope that there's nothing that's changed nothing else that has changed between 2019 and 2020. other than the fact that COVID came and lockdown happened. We should have to hope that, 2019 was not a particularly cold year and 2020 a particularly hot year, and therefore bird numbers have changed. Or one was not a dry year, one was not a wet year, and therefore numbers have changed. And that also brings me to the point made in the study design lecture, which is that suppose we did compare 2019 and 2020, and we found that the average number of bird species reported in a eBird list is less in 2020, April-May 2020 compared to April-May 2019. If you were to conclude that therefore lockdown had the effect of increasing the number of bird species, you would be making a very risky conclusion. Because really all that you've done is you've said that April-May 2020 had more species than April-May 2019, right? Many things could have differed between those 2 years. We have just chosen one thing of interest, which is the fact that people are not moving about. And we ascribe that difference to that. So, but it's risky because other things could also have changed in that year. Now, you could do one better. And you could say, okay, if a 2-year comparison is a bit risky, let's try and see if eBird has data from previous years even. And it turns out it does have. So we can look at, April, May for that part of the country you are in, April, May of, let's say, 2016, 17, 18, and 19, all separately. And let's say all those average number of bird species found in each of those years was somewhere between, in a typical eBird list, somewhere between 15 species and 20 species. Some years it was 15, some 16, up to 20, but that was the range. And then in 2020, that number was, let's say, 25. Just imagine. Now we are getting somewhere. We're getting a little more confident that the number in 2020 is an anomalous number. Because we have a set of previous years. We don't just have one previous year. And an anomalous number, then we would have to say, okay, 2020 was there, looks like it was different from all the other years. Rather than it was different from the previous year, which of course every year is different from the previous year. And slowly we can try and build up an argument or see if it makes sense to build an argument to say that this difference might have been due to the lockdown itself. But I won't say more about it. I can go on and on. There's a lot that can be more refinement that can be done and so on. But I hope you understand the logic and the reasoning over here. What can you infer from a particular result? You have to be very careful. What you want to infer is one thing. And typically we all get, and scientists are not immune to this, we all get very excited about one particular inference that we find interesting or we care about. And we rush to make that inference based on the data and the pattern that we see. But we have to be very, very careful about this. And therefore, as a researcher, what you want to do is you want to, at the research design stage itself, you want to go and tell your friends and your colleagues and whoever else is willing to hear, I'm planning to do this, I'm planning to make this comparison. What I'm hoping to infer from this comparison is what effect lockdown is like. And then you sit back and say, okay, now hit me with your best arguments, your counter arguments, hit me with your full criticism. And hear those criticisms, welcome those criticisms, go back to the drawing board and say, okay, now I understand there's some logic to these criticisms. Let me redesign it in a different way. Rather than doing only one comparison between 2 years, let me look at multiple years and then this year. Let me look another way, by the way, would be to look not only at Delhi, but to say, if lockdown truly had an effect, maybe that effect should be similar in different parts of the country. So let me find 5 or 6 or 7 places where there was a very strict lockdown. And in each of those places, can I compare the previous 5 years with this year? And in every one of those, or in the vast majority of those, if I find that there is a increase in the number of birds detected per eBird list, then again, I'm building up more of a confidence that what I'm seeing is a general pattern. And it isn't something unique to one particular part of the country, isn't unique to one particular year. You know what I mean? So all of these, I hope it makes logical sense to you. Let's not rush to make inferences that we are very happy with. We need to really criticize. And if you're using secondary data, then it's actually fairly easy. If somebody criticizes you, it's easy to go back and say, okay, fine, no problem. I can download the other years. I can download the data from other places and I can rerun my analysis and see if there's a general pattern, etc. But if you're collecting primary data, you are going to the field and collect data. If you do that, then if once you do that and analyze the data and then show it to somebody, it's too late. You can't go back and spend another 3 years in the field collecting more data. And that's why it's particularly important that you get all those criticisms, make sure the logic of the inference you want to make is watertight before you start collecting the data, so that you can incorporate any important criticisms and any important factors in the study design. Because if those criticisms, you only get to know about them after you've conducted your study, collected the data and analyzed the data, then it's usually too late. And people think that fancy statistical analysis can save them and still allow them to make inferences. But statistics are never going to be a substitute for, that is, statistical models and analysis are never going to be a substitute for very careful and very well thought through study design. So if your study design is poor, then no amounts of fancy number juggling can help you. Jugglery. Sorry, I'll say one last thing about this. Do remember that, like we've talked about, there may be more bird species on an eBird list, not only because there are actually more bird species, but it could be because they are more audible. Let's say because there's less noise, and so now people can hear better, and so you can hear birds better. So it could be that the birds. So if you have more bird species in 2020, it could be A, there are more birds around, or it could be that there's the same number of birds, but they're just more visible or audible because human activity has lessened. Okay, so if that distinction matters to you, if you don't care why there are more birds per list, then that's fine. But if you want to know, are there really more birds, or are they just more detectable, then you have to do some additional study and analysis to figure that out. So it's not easy, but then nobody ever said any of this is easy. Akshita says, I don't have any, sorry, people could be more vigilant about their surroundings. Yeah, that's true, Akshita, but we are talking about bird watchers who are doing bird watching and writing down the birds that they see. So by definition, they are vigilant about birds. But it is true, if bird watcher behavior has changed, if bird watchers themselves, while bird watching has changed between before lockdown and after lockdown, then that's another confounding factor. It can give you a potentially spurious result. So you have to be careful about that. I don't have a question in particular, but they're very different and easier to grasp. I see. Oh, I thought they might be more difficult because they're a little more quantitative in nature. But okay, that's fine. That's good. I'm glad they're easy to grasp. Could you shed some light on where we should move ahead from this? So Akshita, that is in the further readings part of it. For this week, for example, I put in the further readings on the dashboard. You'll see, for example, a really wonderful online book called, I think it's called Data Science with R, or R for Data Science, something like that. And it's just a free book. You click on it and you can go through the chapters. There are exercises you can do yourself and so on. So if you want to teach yourself data analysis, that's something. What is harder to get clear guidance on and to teach yourself online is the inferences that may or may not be warranted from the data analysis. It's fairly easy to learn the technical aspects. That here I've got an Excel sheet with data. How do I take that Excel sheet, export it to a text file, import that text file into a programming or statistical language like R? How can I make graphs? How can I, make comparisons, do means, confidence intervals, and all that is fine. But that's really that's the technical part of it. There is an art to science as well, even though people like to separate those. So the art is in the nuance and experience of how you can interpret, or how you should interpret data, and that interpretation is less. I have not found very good, or a number of very good resources on that. Those you're more likely to learn through courses like this, through interacting with mentors who are practicing scientists, and of course by discussing with your friends. So by which I mean colleagues or students and so on. But the technical things you can teach yourself very effectively online. And I've given some resources for that in the extra readings. we can only get closer to the confidence level unless we sample the whole population. We can never be 100%. No, let me phrase it slightly differently, Krishnapriya. If we sample the whole population, then we know what the population mean is without any uncertainty. Right? If I sample all the people in Delhi and I find the mean train length is 115.5, then I know that mean train is 115.5. There's nothing to, there's no uncertainty. There's no confidence. It's exactly 115.5. By definition, if I measure the entire population, then there is no uncertainty. But yeah, that's very unusual. In most cases, we cannot sample the entire population. We cannot measure the entire population. So we have to sample from it. But what degree of precision you need, it varies for the purpose. So you say, how do you say that we are close? It depends on what you mean by close. Some answers we might need only an approximate measure of, but some answers we may need to be very precise. Like, I don't actually know, because ecologists don't think about this enough in my view. When we make comparisons, then we say, okay, I need to be precise enough that I should be able to tell whether 2019 was different from 2020. But when we have single measures, it's very difficult. I mean, you can see by yourself, if I sample peacocks and I say, oh, well, all I can say is that the population, the average tail length in the population is between 50 and 150 centimeters. Then that's a 1 meter span, right? You know that's not sufficient. That's not precise enough. That's ridiculous. You might as well not have done the study at all, right? 90 centimeter span, also not enough. I mean, the tails themselves are, roughly, they're roughly 120, 110, 100 centimeters long. And to have a confidence interval that's 1 meter broad or 90 centimeters is. On the other hand, I know that if the confidence interval has a span of 2 centimeters or 5 centimeters, that's pretty precise. That's really good. But where we want to draw the line and say, I want the plus minus to be about 20 centimeters, or should it be 10 centimeters? That is also a subjective decision, by the way. There is no objective way just for that to say that you succeed if your confidence interval is this much or less, and you fail if your confidence interval is above 20 centimeters of span. That's a subjective decision based on what you want to use the data for. What is that estimate going to be used for? Is it going to be used for some major decision? Just to give a trivial example, suppose there's some park in Delhi and it's supposed to be converted for development, right? And the environmentalists say, no, there are a lot of species here of birds or whatever else, and you can't convert it into some high-rise building or something or the other. And again, this is a trivial example, but let's say the municipality says, okay, fine. If there are more than 100 species of birds, then we agree it's a biodiversity hotspot and we won't convert. But if it's less than 100 species, then we consider there are many other places that have that amount of species, so we'll convert it. So then what you need to know is, you need to have a fairly accurate handle on how many species there are, right? If it turns out that the true number of species, which you don't know, is 110, right? Then you have to, your confidence interval has to be fairly tight. Because I can say, oh, my guess is 110, but it's between 80 and 150 or something like that. Then that's not good enough. On the other hand, if actually there are lots of species, there are 200 species, right? And you have a large confidence interval between 150 and 250. That's a large confidence interval, but that's fine. That's enough, right? Because the lower bound of that confidence interval is still much higher than the cutoff that the municipality gave you. Okay. On the other hand, if and let's not bias it one way, it's possible that there are very few species. Let's say there are only 30 species, but our confidence interval is between 10 and 60. Even then, the upper bound of 60 is far below their cutoff. So there's going to be no benefit in increasing our sample size. So if the estimate is close to some cutoff value, then you need to be very precise. You need to have more and more sample size and get precise. If our estimate in this context is very far from the cutoff value, either high or low, then we don't have to be as precise. So what I'm trying to tell you is that the confidence interval and therefore the sample size and all these things, there's no one answer to what it should be. It really depends on what the purpose is of this study and what the results are going to be used for. Okay, we're back to eBird and birding. More people started birding. Can you shed some light on citizen observations versus actual bird presence? It's not about citizen observations. It's on any, like even researchers, when they go out into the field, let's say they do some transects in a forest. If I do one transect, I might find, let's say, 30 species. If I do another transect, I might add then maybe I see another 10 new species that I hadn't seen in the previous transect. And I do a third transect and I see another 8 species that I didn't see in the first 2. And so as the effort increases, the number of species, unique species that I've seen keeps accumulating. But what happens is after a point, provided the season doesn't change and nothing else changes, after a point, the number of new species I see is going to reduce. So I see fewer and fewer new species until I come to a point where no matter how many more transects I run, I don't see any more new species. So this actually, this kind of pattern happens both in any kind of bird listing or detection, whether it's by researchers or citizen scientists. This is called something, if you plot it on a graph, where you have the total number of species on the y-axis and the effort, let's say number of transects or number of hours spent birding or something like that on the x-axis, then that graph will increase and then, I'm mirrored. Okay, it increases and then it will plateau, it will saturate. And once it saturates, you say, okay, I have a fair confidence that that's the number of species over here. Leaving aside the fact that if we do this only in the day, then the nocturnal species won't be counted and things like that, right? So here we need to be beware of small sample sizes, because we simply may not have detected all the species that are there, especially species that are uncommon or species that may be common but are very hard to detect because they're very small, very quiet, they don't make sounds and things like that. So that principle remains the same. And by the way, if any of you are doing a bird survey or trying to use secondary data like eBird to put together what's the number of species in a place, it's imperative that you also calculate and plot the species accumulation curve or species effort curve. So you get an idea of whether, as the eBird lists have accumulated or as your transacts have accumulated, have we actually reached a point where we can say we've detected almost all of the species over there? Or are we still on that rising part of the graph? Because if the graph is still rising and we've stopped, then we know that there hasn't been enough sampling. There hasn't been enough transects run or enough eBird lists to really arrive at anywhere near the true number. And we have an underestimate of the true number. So that's all I'll just say about that. There's a direct message, but that's just a comment, not a question. Akshita says easier than anything earlier I've studied. Okay, okay, great. Thanks, Akshita. R for data science. Oh, there's a PDF, but I would recommend you look at the Interact. There's an actual web-based book, which I've linked to over there. Great. Okay, we've run out of questions over here. I'll just take one more look at the form. No questions there. And one more look at the discussion group. No more questions either. So I'll give maybe 30 seconds for anybody to type anything else. Capture recapture method. If none of them are equal to 0. So I didn't teach this part, and I'm not. I vaguely remember this formula, but it's not in my immediate domain. So I would ask you to put a question on the discussion group for Umesh, who taught this part. Yeah, I mean, a mathematical formula, that one. So it should be valid only if none of them are equal to 0. Yeah, okay. I won't even attempt to answer this. Yeah. Cool. All right. If we don't have any further questions, I think it's time to get a cup of tea or coffee. Thank you all for coming. And of course, if there are any further questions, put them on the discussion forum. And it's the last few weeks of the course. I hope you've been enjoying and learning. Um, and you'll stick it through the next few weeks. And looking forward to interacting with you guys further. Yeah. Bye.